Good afternoon, everybody, and welcome to Professor Andri's lecture. Today we will talk about geothermal, and I thank Andri for inviting me to speak about it. And I will talk about electromagnetics applications for geothermal. Please raise your hands and send the questions in the chat box. I'm sure that Andri can see them and he can then manage the interrupts. I think it's better to ask questions during the lecture than wait until the very end, because we lose a lot of time going backwards in the slides when we can ask the questions much closer to when I show those slides. So just for those of you that are interested in soccer, I'd like to point out that Germany is participating in the World Cup now just as much as Indonesia, because they won last night and they went out. Haha. So they're no longer part of the World Cup. They're actually now getting ready to fly back in the next few hours. So apart from that, I will talk about geothermal in general. And as normally, I dissect the title. Electromagnetics is a geophysical measurement. Geothermal is the type of application. Geothermal means we're using thermal energy from the earth. When we talk about applications, I'm looking at new and novel applications. Today, I will give you a background and show you some case histories of how we are finding heat sources and what we can use electromagnetics for. And I've selected case histories from Iceland, Hungary, Thailand, Saudi Arabia, and for monitoring. Now, all of you are still very young. And at your age, I got interested in geothermal, and I was taking geothermal lectures and traveling around the geothermal sites in the world. And the interesting part about this is I never put it all in context. And today we have a tremendous revival of geothermal energy. And you will see in this some connections that seem to be very simple, and I'm pointing them out because you need to remember those connections for the rest of your life, because when you're talking about geothermal in the context of Indonesia, you are in the middle of the forest and all you're seeing is small bushes and small trees. You're not seeing the big trees and the different forests. But geothermal is going to be used all over the world in very, very different ways. Now, what are the geophysical methods? The geophysical methods are gravity, magnetics, sound waves, also called seismic, and electricity. And in electricity, we are talking about electromagnetics. And what is electromagnetics? If we, for instance, take a piece of metal, here it's pyrite, which is an ore. It has very little resistance, and if you put a multimeter to it, then it will conduct the electricity. Do not ask Andri to do that experiment for you, because he always leaves the plastic caps on the probes. Try to do it yourself. If you take sandstone, the resistivity is very high, and there's no current flowing. This is an ohmmeter. The same if we replace that pyrite with water, we get a connection. With sand, you get nothing because it's high resistive. So in geothermal, we need water because we want to get hot water out of the ground. So geothermal energy is conductive. It has a lot of current flow, and you can see it with an ohmmeter, but it's kilometers deep. and sand is resistive. Now, gravity is used to see a density contrast and it's very low resolution, but it sometimes can be useful. Magnetics can be useful to define the basin outline, and seismic gets the overall structure. Seismic is the best and most accurate geophysical methods, and that's why it is mostly being used. But the key striking technique for geothermal is electromagnetics. It's the standard geophysical measurements to find fluid zones of higher fluid content and higher temperature, because temperature also reduces the resistivity and increases conductivity. There are some classic papers in electromagnetics for geothermal. One in '74 in a book that every student in the 80s had from Keller and Rappolla. Then one in '83 from Bergdahl and Munoz, 2014. So these methods are standard, there are other papers when you do research. Let's look at the Earth model. In the Earth model, we have a heat source somewhere in the Earth, and then we have some porous material up there where the heat collects and we get geothermal reservoirs. Similar for oil, we have different traps, and we use logging tools, electromagnetic logging tools, and deviated wells. And in a lot of cases, geothermal reservoirs are considered to be in volcanic zones, also in Indonesia, but that is not true. Volcanism is known to be associated with high heat, and that's only because we are looking there first. There is just as much heat anywhere else in non-volcanic zones than in volcanic zones. And I had a hard time to edit some of the slides yesterday, because the author was talking about non-volcanic geothermal reservoirs. But within the context of this lecture, you will see a little bit, or better said in the next slide, that there are volcanic and non-volcanic reservoirs associated with those zones along the globes. Now, what are these zones? These zones are around the plate margins, and these are the plate margins. These are the areas of higher seismicity. And you can see here how the plates are being outlined. And interesting enough, it's all a matter of us going there and looking at it. So these are the areas where we know electromagnetic measurements have been working. In the brown areas, I will give you examples today. So one from Thailand, from the Imperial Valley, Hungary, and Saudi Arabia. But along all of these plate margins, you have in red essentially geothermal fields. These are the deep geothermal reservoirs. The deep geothermal reservoirs means that the geothermal gradient is 50 degrees per kilometer or higher, sometimes 80 degrees per kilometer, and it gets very hot. But the normal geothermal gradient is 30 degrees per kilometer. So we can drill everywhere and get with a 2-kilometer deep borehole, also known as well, already 60 degrees. Now, when you use your shower and you have an automatic thermostat there, then you sort of get a click in the middle of it. And that's the optimum temperature. Those thermostats are calibrated for 42 degrees. Now, that's the temperature you use to take a shower. It's a little bit warmer than your body temperature. If you go a little bit to the right, like to 45 degrees, it is really hot. So in order to get geothermal fluids for usage, it's enough to get a 60 or 85 degree warm fluid. You do not need to get 200 to 300 degrees. like you get along these plate margins. And here in Indonesia, of course, you have a lot of geothermal resources. But the higher it gets, the more minerals you have, because the higher temperature also dissolves more minerals in the rock. And the more complicated it is to produce hot fluids out of the reservoir because of the high mineral content. And you need to get rid of the minerals because they plug up the lines and they make your geothermal energy non-commercial. There are methods we are talking about, and this is magnetotellurics, and another method which is we call controlled source electromagnetics, but magnetotellurics is a passive method. It depends on signals that come from the Earth's magnetic field and meteorological zone, and we can see those here. We can see those here coming into the Earth at the EM plane wave at the northern latitudes, and can actually see those. And it gets in the Earth as a plane wave. And then the higher frequencies appear at the lower depths, and at the larger depths, you have the low frequencies left. You then get a response at a low resistivity reservoir, which is a hot geothermal reservoir, and it heats up porous zones above, which are here. And you measure with sensors that are described here, and we get to that later. They're magnetic and electric field sensors. You measure response, you calculate the ratio to get rid of the need to know the location of the source. You multiply it with 0.2 times the frequency, and you get what's known an apparent resistivity. And the apparent resistivity is essentially a result of 0.2 times frequency times the impedance of the electric field over the magnetic field. Since we measure directionally as a tensor, we can take the X or the Y component and we get measurements in perpendicular direction. How do we calculate the depths of penetration? The depths of penetration, also known as skin depths, is 503 times the square root of the apparent resistivity, also in colloquial called resistivity, but we really mean the apparent resistivity divided by the frequency in meters. So for 1 ohm meter and very conductive sediments, and a frequency of 1 hertz, the depth of penetration is 503 meters. If the resistivity is higher, let's say in Indonesia, you would get in the sedimentary areas, in the basins, the resistivity of 5 to 10. So let's say 10 to be able to calculate the square root easily. So the square root of 10 at 1 hertz is 1,500 meters. So you only need to go, let's say, to 10 hertz to see the upper part, the upper 500 meters. So the frequency band is quite easily handleable, is what I'm trying to tell you. So next, let's look at where the magnetic fields come from. And we have the sun, and the sun sends out solar flares. They are outbursts as a result of plasma fusion. And plasma fusion is essentially when you destroy a molecule into its basic structures and the electrons become free, and the other particles become free, and they get blown out as solar wind, and they hit the Earth's magnetic field and deform the Earth's magnetic field. That's why it's a tail. And then what is happening is, first we have the Earth's magnetic field, we have a solar flare hitting it, it bends it, and behind the Earth, it connects, when it connects, the electrical particles cause polarization and current flow in the Earth's magnetic field in the order of tens to 100,000s of amps. And this current flow then generates a secondary Earth's magnetic field. And you see this as plane wave reaching the Earth, and we actually consider the response to that. So you can imagine that if we have a gravity wave, and gravity waves are coming from black holes, if we have a gravity wave hitting the Earth at, with the magnetic field, we get modulations in the Earth's magnetic fields caused by the gravity wave. This is why some of our sensors are used to measure the gravity wave of the Earth's magnetic field. For higher frequencies, we are not using the sources in the ionosphere, those are low frequency sources. For higher frequencies, we are using the thunderstorms. And this is a map of the thunderstorms from NASA. And we can see here around the equator, and where we have Indonesia right here, there is a high activity. And so you always have very good signals. Now, in those areas, let's say further north here, where you don't have a higher frequencies, or in areas of dense population, like in your case in Java, there is so much power line interference that it's very difficult to measure these small electromagnetic fields. And so you bring your own source. You now generate with the transmitter a square wave and inject the current in the ground in two directions, and you receive on a number of receivers. This is a borehole tool, and these are different receivers. You receive signals that are caused by the switches. And what is happening is you have a current flowing this way, and the induced field goes outwards and downwards with increasing time. And this is much stronger and much easier to measure than the magnetotelluric field. But you can imagine you have to set up this big, powerful transmitter and many receivers at the same time. So the difference between magnetotellurics and when you bring your own field, active source or controlled source electromagnetics, is like this. Here you're trying to see a reservoir or geothermal reservoir or oil reservoir, and you can see it more accurately with controlled source because you don't have to take the ratio of the electric over the magnetic field, and that ratio takes away resolution that you have here on the left. How do we do this? There are different ways to acquire the data. Normally, we acquire all components of the electromagnetic field. Those are obviously 6 components, 3 X, Y, Z components for the electric field, and 3 X, Y, Z components for the magnetic field. Since it's difficult to acquire the vertical electric field, we rarely ever, unless we have borehole measurements, the vertical electric field. So we only acquire 5 components. And in a 3D layout, when we are carrying out very dense measurements, we put out bins. In this case, we have a 20 receiver side bin. We only have one magnetic field. We copy it over to the other sides where we only have electric fields. These are in mountainous terrain where we have helicopter-borne stations or stations where you carry in the equipment to set up your receivers. And these are normal acquisitions line where all components are measured at each line. The frequency band you're looking at is DC to 50 kilohertz. Normally the audio range, and we have a magnetotelluric method called audio magnetotelluric, goes up to 20 hertz. Today, people commonly use it up to 10 kilohertz only, but it really can go up to 20 kilohertz. and 50 kilohertz in order to do other applications. This is the system that we use. It has for normal magnetotelluric range up to 1,000 hertz. These coils then to 70 kilohertz. You have shorter coils, electric field receivers, cables, borehole receiver, and this is a laptop, and this is a transmitter. For controlled source electromagnetics, we have now a current being injected in the ground here, and you can see here at this receiver side, and we have another receiver side. Oops, these are supposed to be on number 2. This is supposed to be on number 3, and this is on number 4. They just moved because I had to adjust those. You can see how these currents are going vertically downwards, directly underneath the receiver side where we are doing the observation. We get most of the information. And here we get it on the 3rd side, and here we get it on the 4th side. So the depths also at which these induced currents go downwards is independent of offset. So at the same time, we get the information from the same depths. And there is some bias towards the receiver location. And that's it for this slide. Now, this is a picture of the equipment. This is a 200 kilowatt transmitter in China. This is one in North America, in California. This in South Africa. And this one again in the US, and we use this also in Saudi Arabia. How do we process the data? We acquire the data, as I said, as a time series, so it's acquired the same way for all methods. And then we do for the magnetotelluric measurements a Fourier transformation, a fast Fourier transformation, and then process the data in the frequency domain. And then we use geophysical inversion to obtain a model. And this model we try to correlate with the geology. The same type of inversion we are doing for CSEM. And there's some processing that's done before averaging. Here, there's no Fourier transformation being done, although you can also do it in the frequency domain. Here's an example of such data set. We have 2 magnetic fields at the bottom and 4 sets of electric fields. Above, the red one is the Y component, the pink one is the X component of the electric field. And these are each 100 meters away. And you can see a signal coming from the ionosphere. You can see in all components. And then you have sometimes noise only in one component. And that noise you can edit out. Some of these spikes, for instance, you don't have this component is very clean, but you see this spike here is going through all components. So it's very good to sometimes look at this data. Unless you do some averaging and smoothing, the data is noisy and it should really be smooth. So after robust smoothing and processing, the data looks like this. And in blue, we have the XY component that goes in the XY direction. And then in red, the triangles, we have the YX component. And if they are the same, the Earth is layered, so-called one-dimensional. If they're different, the Earth is two-dimensional. Here, clearly the Earth is two-dimensional. And the structure is more resistive in Y direction than in X direction. We have seen these equations before for the apparent resistivity. And as I just mentioned, when these components are the same, they're one-dimensional. When they're different, the Earth is two- or three-dimensional. In general, the Earth is three-dimensional. Here is a data set where the components are the same. So the Earth is almost one-dimensional. This one is from Hawaii. Here's the site where the data has been acquired, and it's 4 decades. And I now will go over to the case histories. The first case history is from Iceland. And the objective in Iceland was to map resistive and conductive zones. And I will say more when I talk about the case history. In Hungary, we are looking for hydrothermal reservoirs. That means we are looking for zones of higher water content and higher temperature in a sedimentary section. In Thailand, we are talking about non-volcanic, granite fractured geothermal reservoirs. And notice how I describe this. And when we go to Thailand, I will show you that this is no surprise. The only one that's a little bit surprised here would be Hungary. In Saudi Arabia, no surprise. We are looking for exploration along the edge of Saudi Arabia for geothermal, and there's already hot springs. And then last, I will talk about future applications. And I use some examples to demonstrate what you can do with these future applications. So in Iceland, the entire survey area is volcanic. This is the Krafla area or Sestavik. And there is a power plant that they want to expand. There's only a few people, and there's many, many more sheep than people. So you ask yourself, what are they going to do for the power plant? There are 2 applications Iceland has in mind. They would like to bring cheap iron ore from Scandinavia, put it in smelters, and make steel with low-cost energy. And because of the location of Iceland halfway between America and Europe, they are also putting up server farms, and the sheep in these server farms consist out of computers and clusters that don't need much attention, just like sheep. All they need is electricity. And then they're putting optical cables in between Iceland and America and Iceland and Europe. And then big companies like Google and Apple have big server farms in Iceland. And the 7 people that are manning this power plant will be increased by another 3 or 4 people that are manning the server farm. Now, that is much more efficient than having a sheep farm. Here's the equipment in Iceland, I guess. And of course, there's hot water everywhere in Iceland. And this work was done 2007. Now, we map resistive and conductive targets because within the organic zones, you have change in mineralization depending on depth and fluid flow. And because of the high geothermal gradient, you have quite dynamic fluid flow in volcanic material. And very quickly, a geothermal reservoir can become quite complex. Now, if we look at this in the context of the map, and this is again the Ring of Fire, Iceland is, of course, on the edge of the Ring of Fire. Now, at this stage, I point out Hungary is the only place that's slightly away from the plate margins. Although you have here a plate that goes through here, and you here also have the Arabian plate, and that's why you have in Saudi Arabia geothermal energy. So these are near the plate margins. And of course, Latin America everywhere, and Imperial Valley, where the data for the monitoring is from, is also along the plate margins. And Thailand, which is actually right here, the example, is also an extension of the plate margin, as you can see here, except that the fracture zone here is granitic, where the volcanic material is closer to the edge of the plate margin. And good old Indonesia is right on top of the plate margin, as you experienced with your recent earthquakes. This is the caldera. This is the Krafla caldera. This is the Siskovik geothermal area. And these are roads. and the empty sites were along the roads. You can see that here, that mimics it. This junction right there is like this, and the Krafla caldera would be here. So these are the empty sites. Section number 4 is the east-west section, is something which you will see. I will also show some results from the 3D area, which is right here. The work started with a 500 meters deep loop source TEM interpretation, where they found at approximately 500 meters additional low resistivity zones. But this was not enough to justify increasing the power plant size from 30 megawatts to 100 megawatts. So they needed to know if they should increase the power plant and if there are more chargeable zones in the section. And the data is interpreted using either forward modeling, 3 dimensions, or inversion modeling, and then you go back and forth to get the right results. Here are the results of section number 4, which goes on left from the west to the east on the right. And we can see in 6 to 9 kilometers, a low resistivity zone or a high temperature zone that could charge additional reservoirs that are above. And we look at this differently. Here is the line we are looking at. And this is the line displayed in different colors, where you can now see a more resistive zones here and here. And here is the heat coming up. And that's where the geothermal wells are. And they are all producing. And they are being charged from this 500-meter zone of porous volcanic rock that is acting as reservoir. We'll have at the end a flow model, and you can see a little bit more about the scale. This zone here doesn't necessarily mean that it is a cold, because you could have some additional alterations, chemical alterations, but that's part of the interpretation. This is line 1, and if we go back and look at line 1, where line 1 is, line 1 is section 1 is this line on the left. This is line 1, line 2, line 3, line 4. So line 1 is to the very left, and it's this is a well, and if we look at the wells here, we can see that to 2.5 kilometers, the logs actually see the increase in resistivity that correlates with an increase in resistivity from the logs. Let me just look at the log scale. So the log scale is logarithmic. So this is 1 or 2. This is 2. This is 2,000 meters. This is conductivity displayed, not resistivity. And they say this is 4, and this is 400. So this is, anyway, this is resistive. These scales for the logs are wrong. I'll have to go back to the original report. And the interpretation essentially says that the heat source feeds a hydrothermal reservoir at 1.5 kilometers. And then you have the clay cap above the existing reservoir. I think that's Ford's interpretation. I don't see much reason to have a clay within the volcanic section in Iceland, but that's me. I could be wrong. And then you have the flow in it, and where the fractures have on one side, you have the downflow, and here the lateral flow. where the heat comes in from the right, and you have then the contrast here where you have chemical alteration in this particular rock fed by the downflow and the upflow. So essentially you have two convection cells, geothermal convection cells, and the deep faults are essentially recharging the system on the side. So the fracture zones defines the low resistivity, but these are fractures within volcanics, so they're very difficult to map. And seismic doesn't work in volcanics. And the clay cup acts as seal, which is the reason why you have a shallow reservoir charging the power plant with heat. It sounds strange to me. It's more to me, I would say that the clay cup is representative for chemical alteration than what we normally understand as clay. And it acts as clay electrically. Resistivity contrasts cause polarization and splitting in the MT data. So this means that exactly what I've just said, that means that you have chemical alteration and double layers for mineralization more than from clay itself. Clay is in many cases organic material, and this is clay coming from chemical alteration of rocks. The next case history is from Hungary, and Hungary is rich in low heat entropy geothermal resources, a lot of hot springs, and they wanted to get more hot springs. And so we carried out a reconnaissance of the entire country where our client could get the license. We combined magnetotellurics with gravity and seismic, interpreted the data, the prospects were drilled, and one successful well resulted from this. These are the sites and the profiles. This is the map of Hungary. This is the border to Ukraine, just to give you an idea where we are. And this is a little bit north of the margin that's around Italy and Greece. And we know this is volcanically active. And this goes right through the rift zone. Here we have Saudi Arabia, Saudi Arabian plate, Saudi Arabian carbonate platform. And here we have the African rift zone. And this is the gravity meter at some calibration sites. The MT data was statically corrected and near surface inhomogeneity is removed, mostly to be able to integrate the 2D gravity and the MT data easily. And the gravity gradient was used to get consistent results with the MT. And then the data was inverted at the same time, not jointly, but cooperative. So it's like two people are running different inversion and one person looking the other one over the shoulder. So here we have the data examples and the model responses for 2D measurements along one of the profile. This is one of the lines. This is actually the line that was drilled. And we have the apparent resistivity. The data is calculated usually as apparent resistivity and phase. And the model response for the 2D section is displayed below, and we can see a relatively good match except for areas like here. And here we have the perpendicular line to it, the YX line. And again, we can see a reasonable good match between these two and these two. So this is sort of the quality assurance. We then calculated the residual resistivity and subtracted the regional resistivity, which is the average model for all of the sites. And we were left with some local anomalous resistivity. And the residual resistivity profile looks like this. And that is what we are using to compare with the gravity. This is the gravity. In green is the observed, in red is the calculated to the model. We modify the model such that the red matches the green. It's very hard to display things in gravity because gravity is such an insensitive measurement that the curves always match, but the models can be dramatically different. So that's why I'm displaying this particular one. And you can see here the gravity model superimposed on top of the geologic contours that were derived from the seismic interpretation. And then we also looked at fracture zones. And from the fracture zones and fault zones, we mapped these with areas of gravity and conductivity anomaly. We get first-class anomalous zones and second-class anomalous zones. So you essentially, you're going through the motions of a lot of data and you're defining where you want to go. So this is a geologic section. The well we see later was drilled right here. So this is what we ended up with as target. This is the seismic section. So we're drilling into this structure because we anticipated a low resistivity anomaly right here and a low density anomaly. Low density means that we have higher water content. Water has a density of 1 gram per cubic centimeter. Rock minerals have a density of about 2 to 2.6 gram per cubic centimeter. So low density, since there's no air and no secret compartment in the underground, that only means high fluid content. So you have an area of high fluid content that also is of low resistivity that could also mean higher, higher temperature. And sure enough, it was drilled. And this is the anomaly and the drilling. The target was found within 20 meters at 1,600 meters depth. And it resulted in a 4 megawatt power plant. Next, we are going to go to some surveys done over a number of years in Thailand between 2013 to 2022. And Thailand is right here. Thailand, a map of Thailand. Thailand has about 100 hot springs. And you can see that these hot springs are exactly closer to the continental margin. And we have earthquakes going through here from Myanmar all the way on the western side of Thailand to the north. And in the northern Thailand, near Myanmar, are these hot springs. And we see another map where 4 or 5 of these sites were investigated by the team of Curley, Geophysics, and Mahidol. They actually are producing at one of the area 120 degrees C water, which is plenty for power generation. They used magnetotellurics, audio magnetotellurics, which is higher frequency part of magnetotellurics, and 3D inversion to interpret the data. The results defined a new conductive zone, which was successfully drilled, and they're now planning to do more work. These are you've seen this equipment before. This is the Thai equipment. These are national parks and rice fields. And the depth of investigation is 2 kilometers. So they're looking at 300 seconds to 3,000 hertz. And they also have up to 10 kilohertz. These are the data examples. These are 3D data. And this is an example for a 2D section. The match between the observed data and the calculated response from the 2D inversion. And shortly, we will also see some 3D inversion results. So the work started in 2013, and they drilled in 2019 and had over 200 NT sites. Andri will be smiling because it takes him 3 weeks to do 60 NT sites. But that's Andri, he just doesn't sleep. And so in 2013 was a pilot. They then extended the work, and our colleague Tillman was actually there. This picture here is actually Tillman. So he also did some work in for around Merapi in Indonesia. Tillman did. So Tillman is a very famous man. Not only is his last name man, first name man, but he's also a famous man. And then they found additional anomalies through magnetotellurics in shallow reservoirs, which were then subsequently drilled. And the geothermal assessment is talking about a hot fluid model. They classified 5 of these areas. The 5th one is not shown here. And I have to move your, no. Your faces are above my screen. Okay, well, I guess I can explain it to you. I just won't explain this side here because I can't really see it. So here in the bigger sedimentary basin, you have additional anomalies also in the sedimentary part. So you have a fault system, and in the shallower part, a fracture system. So fractures are within geologic units, and faults are going through multiple geologic units. And they're fed by a hot granite at depths, and the fractures are feeding the heat, and you have fluid circulation that is recharging the reservoirs. And so they're trying to find the sweet spots in those reservoirs. Here's one of the original examples from Pham Hot Spring. There's been a lot more data being acquired. I didn't include the more detailed slides. And I only took one of the multiple case histories. But essentially, the Phang Hot Spring shows you that it's 3D, and this is a new geothermal reservoir. They did more denser acquisition. And you can see this is much sharper than the previous one. So here you can see that there's actually more anomaly here, and they already have a small geothermal plant in place, and they're trying to get more. And this is then the edge to the basin, where you have meta sediments, which are essentially alterated sediments, and this model is not correct. You cannot have meta sediments like this and then fractured granite inside the meta sediments, because granitic intrusions have a much smoother edge than that. So this should be, if this is really fractured granite, then the meta sediments stop right here and they come like this. You can't have this much details in meta sediments because metamorphosis, not metamorphosis, the conversion of the meta sediments from sediments to hard rock is done over larger volumes under heat and pressure. And when it comes up, it is not fractured granite, it would be fractured meta sediment. So this may or may not be granite if this is granite. And these are fault zones. Now, this does not make sense. When I looked at this and presented this before, this did not make sense. And only after this lecture it made sense. And 3 slides from now, I will explain to you what makes sense about it and why this is different. So you have little hot springs already, but you're trying to find the area where you can drill so you can charge a power plant. And clearly, these are the references. I've put them in here so that you have them. And next, we are going to Saudi Arabia. But before we go to Saudi Arabia, let's go to the beginning of the slide. The slides are flipped. So this is Saudi Arabia, and we have a rift zone here. So this is a very deep, the Red Sea is very deep. And what you have here is the eastern side, which is the side along the East African ridge here. Notice this, you have earthquakes here. These are the plate margins. But we all know we have an open crust right here because we have lava coming to the surface. So this is the Kenyan rift zone. So there's more in here. So clearly this part is not well understood. So let's get back to Thailand. So what I told you in Thailand, you have an extension of the plate margin going this way. And if you have the heat zone at the bottom feeding it, that comes directly from the lava at the plate margin, then you will have large granitic blocks. And you could have metasediments above, but metasediments are essentially cooked sediments converted to hard rock under temperature and pressure, and then pushed up. And I doubt that there's anything pushed up right here. This is the area. So I think what you have is you have just granites and maybe some intrusions, but you don't really have any type of subduction zones or overthrusting. So in Saudi Arabia, as we looked at the rift in Saudi Arabia, we have a hot spring on the eastern margin of Saudi Arabia, and right next to the Red Sea is over to the left. We have a valley, and there's a hot spring right here. These are the magnetotelluric sites. The objective in Saudi Arabia was a test survey to get ready for a CSEM survey. This is the hot spring. You can see the hot spring here. It's quite hot. You burn your feet if you go it. And this is a 2D inversion profile. And you see here is a geothermal cell. And this is the location of the hot spring, and this is the interpretation. Essentially, the convection and recharges. An early interpretation was done by this. You have a thermally insulating layer, and then here you have a fracture, and the heat is coming up. So the objective of electromagnetics is to understand what is happening around these fractures and see sweet spot forms. So this is the fracture zone. But clearly, you should drill here because you have more hot fluids in this area, and you have larger geothermal potential. And maybe even here, not just necessarily where the water comes out at the surface. So you have much higher opportunity to get more geothermal energy. They're preparing for a CSEM survey. This is the CSEM transmitter in Saudi Arabia. And this is the test in the field. These are the receivers, and they use the same equipment for magnetotellurics. The punchline is that CSEM has higher resolution than magnetotellurics. CSEM servers are more complex because they use transmitter and receiver. The expiration value is mostly in complex environment in areas with a lot of noise. The big value with CSEM is you can get much better borehole ties. And for production, you can monitor cooling zones And for induced seismicity, you also use monitoring of the geothermal reservoirs. The mandatory part with CSEM service is that you do a feasibility and a noise test, and you tie your measurements to the logs. And we will look at that in the next monitoring example. And the next monitoring example is going essentially through a workflow where we define target objectives, and you use all geologic information, the well log, the geology, seismic data, any geophysical data. You do noise measurements in the field, like here, noise measurements from the Imperial Valley. On the right side, this equipment was in North Dakota. Then you calculate from the noise measurements a noise spectrum. You can process that spectrum, and you define a noise level. And this noise level is used for the 3D modeling. The model itself is derived from well logs, and we'll see an example in the next slide for that. And then these models are varied. Like in this case, we have a transmitter and multiple receivers. The blue one is this one, and these are the transmitter and receiver curves, and these are the power spectra. These colors are not correct, but it gives you an idea. The colors change with PowerPoint. And when they have to convert it to pictures, you can't change them anymore. So I apologize for that. And no, this is from North Dakota and this is from the Imperial Valley. So these colors are correct. These colors correspond to this. And this is a similar example from a different location. So we've done the same procedure in multiple locations. And then you look at the noise level from different sensors, and you use that sensor that has the lowest noise level and covers it. You change, like in the geothermal case, the temperature of the reservoir. We use it to monitor production changes. And you then go ahead and see if you can measure this. And then you can modify the way you produce your reservoir in order to optimize your production and increase efficiency. Here is an example for a reservoir at approximately 3 kilometer depth. And this reservoir has lower resistivity. Actually, this reservoir is higher resistivity. So this is, in this case, a sweetwater reservoir in a produced geothermal field, whereas the geothermal field would be the blue one. This would actually be a very good schematic for the Imperial Valley as well. And then you have on the right side the logs, and you calculate equivalent logs, anisotropic equivalent logs, and you use these to match with your data and your inversion. And this is how you can calibrate your surface measurements to borehole measurements. You then study the variations depending upon the radius of your reservoir plume. And here your reservoir has consists out of sweet water in a saline reservoir. Now the Imperial Valley has resistivities below 1 ohmmeter in the geothermal reservoir. And that's because it's below the sea level, and the entire section has a lot of salt in it, and a lot of the water has been evaporated over time during the depositional times. So what we have here is the percentage variations for the different fields. This is the X component, the Y component, and the magnetic field component. And we can see different percentage variations at a certain time. And this is the signal in black, and in blue is the noise. And we have the same on the right side. When the re-injected water has not been, we have less re-injected water. We are producing a geothermal reservoir from the flanks of the water injection. And that is not normally clear because a lot of times you just produce where you have the wells and you re-inject away from the wells and you're hoping you're doing the best. So including the structure and using seismic is very important. And optimizing this and understanding this is very important. And so we need to continuously monitor the production in order to see the small changes. And this essentially means that we have to install more equipment. And here's an example. If you do this correctly and calibrate your data correctly, you can actually match 2D inversion results. These are 2D inversion results. These are this is 2D MT inversion. This is 1D CSEM inversion. This is the reservoir at 1.6 kilometers, which would be right here. And you can see again that MT is sort of fuzzy. CSEM is more accurate. This is at 3 kilometers. And these are the 3D models. The 3D models are matching the data very nicely as well. In summary, we've reviewed EM methods, magnetotellurics, and CSEM. I have mostly reviewed land methods. We use normally magnetotellurics for background measurements and CSEM for details. Both are key in exploration, production, and monitoring for geothermal and oil. Calibration is mandatory, and the challenges are always in the data integration. And as equipment, you need an array acquisition system and high power transmitter. And we all know that the geothermal market is growing very quickly, and it'd be very interesting if our predictions become true. In the future, we will see denser data, seismic EM combined. EM will be used for monitoring and better integrated together. And with this, I would like to thank you, and I'm open for questions.
Okay, thank you, Kurt, for the very interesting.
Oh, I have one more diagram.
Oh, okay.
So
go ahead.
we have now looked at standard measurements for the surface. That's what we are doing. When we integrate this more with a borehole, the value will go up. So you have a hard time in Indonesia finding jobs with the geophysics degree, but there will be more jobs. And when you make repeatable measurements, there will be more jobs because the asset value, because of using electromagnetics or geophysics, will always be increasing. And when we permanently install our sensors, we will have a lot of jobs for geophysicists.
All right, that's all?
That's it.
Okay, thanks. Okay, anyone want to give questions? Ada yang mau bertanya? Yeah. You can raise your hand if you want to ask a question. Okay, maybe before they ask, I really interested. It's really interesting to ask you the questions about the geothermal system that you saw up from the Saudi and also I see from the Europe ones. So what type of the cap rocks that they have there? Because I couldn't see, mostly in Indonesia, we have the clay cap, which is the conductive. In most cases in Indonesia, the clay cap is more conductive than the reservoir itself because of the clay content and then also the minerals in that particular. I mean, in the reservoir and then also in the clay is different. So how about in the Europe and then also in Saudi that they have a difference? What I see. It's different. It is they have a different system of the geothermal. Can you say something about that?
Well, you know, you're doing the same thing that I was questioning before to call a seal of a reservoir clay cap. I think that's a geophysical term. And clay comes in many, many different forms. Around a salt dome, you have a clay solver that can be less than 0.5 centimeter thick. And in CSEM measurements, you can see it as 100 meters thick, 1.5 ohm meter layer, because it's so conductive. It totally depends what type of alteration you're dealing with. So we call it clay in some form because we have polarized material that is very conductive and that attracts water and seals at the same time. So I understand that you have that in Indonesia. But when you come from the oil environment, a clay cap is mostly organic material, and it's different. So the problem with the clay cap is once you have a very once you have a very strong conductive layer, it is very difficult to see the layers below. And so very quickly, magnetotelluric will only see the total conductance. And you will have to go to controlled source EM measurements quicker to differentiate more. The best way to solve these problems is not from the geophysical side, but to have a borehole and calibrate your geophysical measurements against the borehole. So using geophysics as magic one to find, to explore for geothermal may not be the best use of geophysics. It's much better to use geophysics to understand your reservoir.
All right, and the casing from Saudi, what the type of the cap rock there? Is it the volcanic or kind of the more resistive rocks? Sky might be the shell or whatever. I don't know what they expected to as cap rock.
The overburden rock are sediments, and below are volcanoclastics. So volcanoclastics is a mixture of volcanic material with clastic material, sedimentary material. So what you have in Saudi Arabia is under all of the Saudi Arabian peninsula, you have the Saudi Arabian carbonate platform. And on the left side, you have a rift zone, which is a very steep rift zone, where the whole platform has been pushed up. And that's why you have volcanoclastics, a mixture of clastic material with volcanic material along that rift zone. So the thermally insulating layer is not clear what material it is. They have to drill more wells, and they're planning to drill more wells to understand that. So this is what, I cannot answer your question because this is unknown.
Oh, all right. So, okay. Yeah. I also see from the Thailand case, it's actually similar to one of the geothermal potential in one of area near the Singapore, the part of Indonesia. It's called Bitung, Bangka Belitung, and they have the same geothermal system, which is the thermal is from the granitic rocks. And one of my friends have measured and doing the research there. They say that the thermal is probably from the how can I say it's not from the granite itself, but it's from the how can I say the material that can produce the heat. It's like the atomic that produce the heat, and but I'm not really sure about that.
Yeah, this is a system. You have hot granite, which is your heat source. In this case, in Indonesia, you have essentially a fractured zone, as we saw before, where you have hot material from the mantle coming up. That builds plumes below the surface layer. This is the granitic layer, and then you have fractures in the granite. And then you have different granitic zones around it, and you need to find sweet spots within it.
All right. So about the in Thailand, I could not also see what the kind of the cap rock they have, because they have very slow, very shallow reservoirs, and I see also the temperature is quite low compared to the geothermal potential in Indonesia. It's only 120 degrees, which is not really for height, which is the height high geothermal temperatures is more than 200 C, right? I mean, in order to produce the steam waters, which is contained with a lot of material and then also chemical stuff, and the the boil water will be increased. I mean, the temperature in order to the water to be evaporated to produce the steam.
Nobody is trying to produce steam in Thailand. They're happy with hot springs for various purposes. They have a permanent heating system outside called the sun. So I don't think they need much heat for this. But they want to use heat exchangers where they are increasing the temperature of the fluids to drive turbines to get electricity.
Oh, okay. All right.
So nobody's after steam. The reason you are only with EGS after steam for other low enthalpy geothermal reservoirs. And in Germany, everybody has a geothermal well in the backyard and they only get 70 degrees and they put a heat exchanger in and they just heat their houses with it, produce some hot water, produce a little bit of electricity, which they feed to the grid, and they're living for free.
Yeah, I got it. Yeah, I know that. Yeah, but I mean, most of the electric productions in Indonesia, we use the steam water in order to generate the electricity. So yeah, okay. Thank you for the
because you are at the ring of fire. You are right on top of a high enthalpy geothermal reservoirs. You're talking about 200 to 300 degrees reservoirs. You're sitting in the fire. You're not worried about these low enthalpy reservoirs.
All right. Okay. Thank you, Kurt. Anyone want to ask question? Ada yang bertanya? Okay, Sumi student is quite.
They're sleeping. They had just had lunch.
No, they had their lunch. Okay, ada yang bertanya? Nessa, Fernando, or the others? Abdul? Just ask question. Maybe you can ask the job about the geothermal in the future, or probably you can find the job either in Indonesia or outside the country. Ada yang bertanya, silakan ditanyakan apa aja gitu ya. Ada? Bisa bahasa Indonesia, nanti saya coba terjemahkan kalau ada yang mau. Okay. Anyone have question?
Mungkin saya bertanya, Pak.
Okay.
Pak bantu translate, Pak.
Okay, so he will ask in bahasa, so I will translate to you afterwards. Yeah. Go ahead.
Mungkin yang pengen saya tanyain, Pak, tadi kan Bapak juga ngebahas mengenai yang tadi clay cap, Pak, yang tadi itu, Pak. Jadi kalau misalnya kita lakuin pengukuran di Indonesia, misalnya kita lakuin pengukuran di Lampung ya, Pak, yang kita bisa ngomongnya clay cap di Indonesia itu yang Bapak bilang tadi berbeda sama yang di negara yang dibahas Mister tadi. Jadi di sini kalau misalnya kita melakukan pengukuran radius yang bisa dilakukan dari pengukuran elektromagnetik ini sekitar berapa meter atau berapa ratus meter sih, Pak, apabila kita melakukan pengukuran?
Areanya maksudnya luas areanya atau bagaimana?
Iya, Pak.
Oke.
Iya, luas area, Pak.
Okay. Okay, cool. So he asks about the area of the measurements in electromagnetic. I mean, how what the areas that we should measure in order to get to the clay cap or to the reservoirs. He asks about that. Do you get my question?
Yes. Usually in geophysics, you take twice the aperture. What does that mean? That means if your depth is 2 kilometers, you'd go straight to the surface and you measure 4 kilometers to all sides. So you measure in a circle with a radius of 4 kilometers around your target if you want to go to 2 kilometer steps. Now, this controlled source, you can reduce that a little bit, but that's a very good rule of thumb.
Oke, thank you. Oke, jadi umumnya itu 2 kali lipat dari kedalaman target kita ya. Jadi misalnya targetnya 2 km bisa luas jauhnya itu 4 km. Ya seperti itu. Kalau misalnya areanya berarti bisa 4 kali 4 16 km. Abdul. Oke? Abdul, is that okay? Oke, ya, ada lagi yang mau bertanya? Anyone? Ini kesempatan nih ya buat nanya langsung ke expertnya.
Pak, saya izin bertanya, Pak.
Oke, ya, go ahead.
Tadi kan kalau nggak salah di slide itu bilangnya kalau misalkan metode CSEM itu lebih bagus resolusinya daripada MT. Nah, cuman yang saya tanyakan di sini, kenapa yang paling banyak digunakan paling umum gitu, Pak? Itu metode MT atau memang karena metode CSM ini belum dikembangkan lebih jauh gitu, Pak?
Okay, thank you. Yeah, Kurt, I got one very interesting question about the why mostly they use MT in the geothermal exploration, not CSEM. You already say that the CSEM has higher resolution than MT, but why people choose MT instead of MT? Or instead of CSEM, sorry. Yeah,
it takes decades for a method to be introduced. The techniques MT and CSEM were routinely used in the 1980s for geothermal, and then they were both not used. And the only method that was left over is magnetotellurics. And now everybody's doing magnetotellurics, and it's well established. There's equipment everywhere available. As far as high power CSEM is concerned, there's no real system available except ours. And there need to be service companies that are applying this and demonstrating this. So now in Saudi Arabia, they're going to test it and apply it, and there will be an interest afterwards. But it takes decades to introduce new technology, not just a few years. So I've been trying for 10 years to get Indonesia to do this because it will solve a lot of problems. But there's always a question of money because the equipment costs at least $1 million. And of course, nobody wants to spend the money, and so nothing ever happens. But CSEM was done. I can show you where CSEM was done since 1970s by going back to the original slides. So CSEM was done in the Imperial Valley. The Brawley geothermal field, which is a 30 megawatt power plant, was found with CSEM. I did several surveys there, and the picture you saw from the equipment was actually from 1981. And I'll show it to you. So this is the Imperial Valley. This is near Imperial, the town of Imperial. This is the haystack. And this is actually the Brawley field right there. And this was 1981. So it's very old, was standard. And going back to that other slide, then the geysers in Northern California, the geysers geothermal field, very well known, was also found with CSEM. We used the megawatt transmitter with 3,000 amperes. High power transmitters were considered dangerous, and I published everything in 92. And for a short while, people were making equipment, but then they stopped doing it because they were afraid of it. And now our system is very safe. So also in New Zealand, right here is New Zealand. George Keller did measurements in the 1970s with CSEM. for geothermal. We did it for oil in Australia, not for geothermal. And then there was more work done in Idaho, which is here with CSEM. There was some CSEM work being done in Italy, not really published. In Germany, I did some work in Germany, now in Saudi Arabia, no work in South Africa, but not for geothermal. So we did work here in South Africa for CSEM, where the cap carton is. And no CSEM work in Latin America. There was some work done in Nicaragua, but that's lost interest. In Idaho, Colorado, Iceland. The lady who did the work on the Krafla, where now there's a power plant, she finished the survey. By the time she interpreted the data, there was a volcanic breakout, and her survey area was covered. So what you saw in the picture with the power plant right here, this is the Krafla caldera. This is where she did CSEM work. And then there was a volcanic breakout in 1980, and now they have a power plant there. So people have been using CSEM, but it's very difficult to make the equipment. And only now the equipment is reliable and repeatable. So it's just a matter of everything takes time. So people will be using CSEM more as they understand it more. And only now we have the computers to do the 3D modeling correctly. So, okay. And nobody else but us can obtain the resolution at borehole scale for CSEM measurements. So it's been used since the 1970s, but it's still a relatively new technology.
Okay, that's all good?
Yes.
Okay, so let me explain bahasa. Singkat saja ya. Jadi tadi dikatakan bahwa salah satunya itu karena alat yang lebih available sekarang banyak itu MT ya. Jadi walaupun sama-sama dulu digunakan untuk geothermal, tapi yang banyak digunakan itu MT. Salah satu alasannya itu karena lebih murah ya dibanding CFCM. CFCM itu ada transmitternya, dan transmitternya itu jarang orang yang bisa produksi ya. Jadi itu alasannya kenapa saat ini MT lebih banyak digunakan. Nah, daerah-daerah yang lebih noise ya biasanya tadi yang sudah disampaikan ya bisanya menggunakan bagusnya sih CCM gitu ya, tapi karena harganya lebih mahal jadi banyak menggunakan MT. Ya, sudah ada contoh kasusnya tadi disampaikan. Oke. Leonardo?
Cukup, Pak. Terima kasih, Pak.
Ada lagi yang lain? Silakan. Kalau ada yang mau bertanya? Oke, nggak ada. Okay, Kurt, I think there is no more questions left. So I think this is the end of our lecture for today. And I do appreciate for your presentation and also the information that you give to my students. And they are all interested in studying geothermals. So this is the class special for the geothermals. And I hope in the future, as you know, Indonesia also now trying to explore more geothermal potentials, including in our area here in Lampung. I just went to the officer of mineral and energy departments yesterday, and we talked about the potential for the geothermal in Indonesia, and then he said that there will be more the use of the geothermal for the energy resource, and but it's still waiting for more funding for sure, and then also more company to exploit to produce the geothermal here in Indonesia. So actually we have at least 5 geothermal potential here that already and ready to produce, but still waiting for the company or to produce the geothermals. Yeah, it's all about the money and to do so. All right, and I think this is the end of our lecture for today. And again, I'm very yeah, I thank you so much, Kurt, for your time. And I hope in the next week we will meet again in another class. So actually for this class, for the geothermal, we have 2 classes, and you will give another class next week. All right, and thank you everyone for attending this class today, and we'll see you next week. Okay, and
thank you, Andre.
Thank you so much, everyone.
And we'll talk later. Thank you.
Good afternoon, everyone. Bye.
Good afternoon. Bye-bye.
Thank you. Oke, terima kasih semuanya ya. Untuk tugasnya tetap dikerjakan ya. Nanti kita akan cek lagi minggu depan.
Baik, Pak.
Oke, iya. Ada yang mau ditanyakan nggak? Tadi nggak ada yang bertanya soalnya. Cukup ya, mungkin karena bahasa Inggris. Jadi ya belajar bahasa Inggris karena kedepannya mungkin ya kelasnya kita sudah internasional lagi gitu ya. Sekali-sekali bahasa Inggris supaya semuanya refresh kira-kira ya. Termotivasi untuk kedepannya seperti itu. Karena kalau kita semakin banyak skill ya, kalau bahasa Inggrisnya bagus, saya yakin kerjanya juga akan lebih baik ya gitu ya. Jadi itu sedikit trigger juga kenapa saya invite orang luar ya untuk mengajar di kelas kita biar sedikit termotivasi lah ya. Oke, terima kasih semuanya ya. Mungkin cukup sampai di sini pertemuan kita untuk hari ini, dan kita ketemu di minggu depan. Tugasnya sementara dikerjakan ya, laporannya jangan lupa diselesaikan. Kita ketemu lagi minggu depan. Terima kasih dan selamat sore semuanya. Sampai jumpa di minggu depan.
Selamat sore, Pak.
Sore, Pak.
Terima kasih, Pak.